4.5 Linear Approximation and Differentials. In this video, we will focus on linear approximations. To start the discussion, let's first talk about the tangent line to the graph. Recall f prime of a is the slope of the tangent line at the point x equals a. If you have slope and a point, it's quite easy to find the equation of a line. So let's use the point-slope form of the equation of a line. Remember, our point is a, f of a, and our slope is f prime of a. Solve for y. After we solve for y, what we get is the equation of the line tangent to the graph at the point a, f of a. We're going to call this tangent line L of x. Notice by the graph that if x is near a, then the tangent line is approximately equal to the function. For that reason, L of x is called the linear approximation of f of x near a. We're going to use this information to estimate the square root of 1.1. We don't know what the square root of 1.1 is, but we do know what the square root of 1 is. So we're going to construct a linear approximation at 1 and then use that linear approximation to approximate square root of 1.1. Again, we're choosing a point near 1.1. We're choosing a point where we actually do know the square root. So that's why we're choosing 1. Our function is f of x equals square root of x. And recall that can be written as x to the 1/2 power. Take the derivative, the 1/2 comes down, and then you have x to the negative 1/2. And when the dust settles, you get that derivative. Okay, a is equal to 1, f of 1 is equal to 1, and f prime of 1 is equal to 1/2. Put all of this into our linear approximation formula. Those are the pieces. Put them all in. And we get our linear approximation is equal to 1 plus 1/2 times x minus 1. Which you could rewrite to 1/2 x plus 1/2. But there's no need to. I just happened to do it. If x is near 1, then this linear approximation does a good job of approximating the function. Since 1.1 is near 1, we can use this linear approximation to approximate the square root of 1.1. Square root of 1.1 is approximately equal to the linear approximation at 1.1. But the linear approximation at 1.1 is just 1/2 of 1.1 plus 1/2, or 1.05. You can see with an Excel spreadsheet that the square root of 1.1, you get about 1.048808848, which is pretty close to what we got. So our approximation was not too bad. It was not bad. And all we had to do is take a derivative. Now, would this linear approximation be helpful in estimating point 1? Look at point 1. That's down near 0. And our tangent line was created at 1. No, not at all. Point 1 is too far away. This is not going to work at all. We want a different linear approximation. We want to choose a point much closer to our target point of point 1 and make a new linear approximation. Now, the point we want to choose has to be a perfect square. You might remember we choose a perfect square. We choose something we actually know. So what perfect square is close to point 1? Of course, 0 is, but we can do better than that. A good choice is 0.09 because 0.09 is a perfect square and is also close to point 1. So let's find the linear approximation for the function at 0.09 and use that to estimate the square root of 0.1. We've already done this once before. First let's evaluate the function at 0.09. So we've got 3/10. And then let's evaluate the derivative at 0.09 and we get 10/6. Set up the new linear approximation. And for y equals the square root of x and a equals 0.09, the linear approximation is given right here. Since point 1 is close to 0.09, this linear approximation will approximate the square root of 0.1. And the linear approximation at 0.1 is about 19/60, or about 0.3167. So we were able to find a good approximation of 0.1 using derivatives and simple arithmetic. And that's how you use a linear approximation. In part 2, we'll switch over to differentials. See you then.